Uh, hello, hello everyone. Today we have the 10th talk in the colloquium series. First of all, I would like to acknowledge the traditional owners of Australian land and pay my respects to the elders past and present. Today, I'm happy to present Susan Coppersmith, who is a professor and the head of school at the University of New South Wales. She's one of the leaders in qubits and quantum computations technology. Susan has made her PhD in Cornell in 1983, and after being a postdoctoral fellow at Brookhaven National Lab, she joined Bell Laboratories, where gradually became a distinguished member. In 1995, she became a professor at the University of Chicago, and in 2001, she moved to the University of Wisconsin Madison, where she was a professor and the department chair. And so very recently, in 2019, she moved to Australia, where she's to the Sydney, where she's professor and the head of school now. Susan has numerous awards. I will just mention a few. She's a member of National Academy of Science, fellow of Australian Academy of Science, fellow in American Academy of Arts and Sciences, and many more. Okay, Susan, please feel to start and we will enjoy the talk.
Okay, great, thank you. So I just want to say that before I start, well, first of all, thanks for the invitation and thanks for taking the time to listen. And if you have questions, I'm happy to do questions, during the talk. You can interrupt if you want, or you can put them in the chat, and I will try to check the chat. And Dimitri, if something's in the chat and I don't see it, feel free to interrupt.
Don't worry. I will moderate it.
Okay, great. Okay, so I'm going to tell you about quantum stochastic resonance, and actually the experimental work I'm going to talk to you about is quite recent and was published actually just like a month ago or 2 months ago in Science Advances. And so in that sense, the work is quite current, but the story is actually a long story. And I will tell you the story for reasons hopefully that will become clear. And one of the things I find really interesting about it is that the fundamental concepts that I'm going to tell you about are really relevant to many, many systems. And as a theorist, I find that really interesting. So I'm going to start with this is the outline. So first I'm going to tell you about what stochastic resonance is. I'm going to assume you don't know what it is. And so I'll give you a short introduction on what it is. And the origin of stochastic resonance is actually to explain the periodicity of the Earth's ice ages. And a classical system, classical complex system, and stochastic resonance has been shown to be relevant to many, many classical systems. And the work that I've done has been extending the concept and understanding the applicability of the phenomenon to quantum systems. And so I will give a little love to some work I did quite a while ago. I realize many of you were not born, where we showed theoretically that stochastic resonance applies to quantum systems, can be applied. And then recently, I became aware of work actually in a seminar that was sponsored by Fleet, by work in Stuttgart, where they were measuring it. And so then we started collaborating, and I hope you're convinced that really, I think that it's very convincing that it happens, and theory, I think, can really play a big role in being able to extend the system. The system is single spin transitions in iron, and so really relevant to spintronics, and so hopefully stochastic resonance will turn out to be relevant in nanotechnology as well. So let me get started and tell you about stochastic resonance. And it was the concept was come up, was originated in the early 80s. And one of the reasons I decided I should talk about this is that one of the originators, Giorgio Parisi, was just awarded the Nobel Prize. And it was not basically for this work, but it is part of his opus and is considered one of his top 10 contributions. And so therefore you will know one thing that Parisi did that why he's considered a great physicist. So first I'll tell you about this original motivation and the ideas that went behind that. So the motivation was they were aware that Benzi, Sutera, and Volpiani also mentioned. Okay, they were aware that if you plot, if you look at the Earth's climate, it went through ice ages, and this is a power spectrum of quantity that is correlated with temperature. Specifically, it's the amount of the fraction of oxygen 18 in ice cores. Okay, but the sum time series, you Fourier transform it, you square it, you take a power spectrum, and you see this big peak at roughly 100,000 years. And so they were saying, well, what causes the ice age? And they noticed that that period of 100,000 years matches that of the variation of the eccentricity of the Earth's orbit. And that's just the statement that the Earth goes around the sun, but there are other planets, and those planets perturb the orbit. And there's, and the eccentricity, which again is like circle has, no eccentricity, and then ellipse has, as it flattens, the eccentricity goes up, and that fluctuates on a scale of about 100,000 years. And that has a small effect on the amount of radiation that hits the Earth's surface from the sun. But it is on the right scale. And they said, well, it's a really small perturbation. They did the estimate, small perturbation, but it has the right period. And they said, but maybe there's something that amplifies the noise. And their idea is that noise, meaning all the fluctuations in the Earth's climate, they call noise, that the noise amplifies the small deterministic driving. Okay, so it's stochastic resonance because the noise is enhancing response to a driving. Okay, so, and the canonical picture of stochastic resonance, which is where everything I'm going to talk to today is, going to fit in this picture, is that basically that you think of there are two states in the context of the ice ages. There's a cold state, there's a hot state, and then there's this little driving that, here the cold state is, more favorable. Then you go here, the hot state's more favorable. And the question is, do you make it over this barrier when you have this little driving? And what happens is that, now this is just a numerical simulation of a differential equation, but it tells you what happens is that here you are and your system's on this side. And now the question is go over to the other side. And if the temperature is low, if the noise is low compared to this barrier, and we're going to call the barrier height U, and we're going to think of this as an energy. If you can get over the barrier, you'll go to the other well. But at low temperatures, you just can't get over the barrier. Okay. At high temperature, this thing is sort of where the thing would, where this particle would hang out in the absence of drive. Okay. At high temperature, it just goes back and forth and it doesn't care. And it's not synchronized to the drive at all. But at intermediate temperature, then you get the situation where you can sort of pull out the drive frequency. Okay, so you go over here, the noise just gets you over the well, comes back, and then you get a maximum response caused by the noise. So so pretty early on, as you can see, this is quite soon afterwards. Fove and Heslow did a very simple experiment using electronic circuit, and they added noise to it. And this is the signal to noise ratio, which is, again, you put on this little signal and you say, well, what comes out? What's the signal that comes out? And of course, the noise goes up because you've added noise to the system, but the signal goes up much more so that the signal to noise ratio has a maximum as a function of the noise amplitude. So again, that is what stochastic resonance is. You add the noise, you get this resonance, meaning a maximum. All right. Now, for what we're going to do later, when I finally get to the 21st century, we're going to do an experiment where the thing that they calculated was actually sort of how long you are in each state. Okay, so if you're in the left and the right and left and the right, again, you synchronize to the noise, and so you get these peaks. And And these peaks, the analog of these peaks for the quantum system is actually what we're going to do. So I wanted to show it again, but in the classical case, there are these strong peaks, and that is another diagnostic for stochastic resonance. Okay, so now I'll first tell you about the work that I did like way back when. And that was Ritva Lofstedt, who was a student at the time. And I asked the question of everything that had been done in stochastic resonance up to that time was for classical systems. And there was this picture of you go over the barrier, and your probability of going over the barrier has this exponential dependence on the temperature, or which is synonymous to the noise and what I'm going to talk about today. And the thing is, in quantum systems, quantum tunneling means that you don't have to go over the barrier. You can tunnel through the barrier, and at the lowest temperatures, the tunnel rate goes to a constant. It's independent of temperature. And so the first thing you might think of is that stochastic resonance really requires going over a barrier, some strong dependence to this transition rate, and therefore it won't happen in quantum systems. But we happen to notice that if you generalize slightly to the case of systems where the minima are not at the same energy, then the rate that goes from the upper to the lower is independent of temperature. But the one that goes from the lower to the upper, that does depend on temperature, because you have to go uphill in energy. And that is sufficient to have very similar phenomenology. So again, if the temperature is really low, then again, now you're modulating this potential a little bit. And if you modulate it, you still can't go uphill. And so you stay in the lower well. If the temperature is really high compared to the asymmetry, then you're always equally populating both wells, and putting a small modulation doesn't matter at all. But then there's this intermediate temperature where you do get a really big response to small modulation in the asymmetry. Okay, you also can modulate the temperature. You can either modulate the noise or modulate the temperature, and you get very, very similar phenomenology. And then also we worked out a theory of the whole thing, and I only put in a slide, but I sort of a couple of slides at this point in the talk. Hopefully this will not be a problem for you. But the way you actually set up the calculation is you say, well, look, we just have transition rates that go back and forth between the two sides, and there are these rates. And the big assumption that you make, and essentially the only assumption that you make, is that the transition rate, first of all, exists, and then second of all, does not depend on how long you've been there. So the system is memoryless, that if you were in the right side, there's some probability that depends on where you are relative to the drive. It depends on the time, but it does not depend on how long you've been in the state. It doesn't have a memory of that the transition rate finds its value on a scale much faster than the drive frequency. And if you do that, then you can write a differential equation for where the system is. Okay, and it turns out that you can do an essentially complete analysis of that. And in terms of these rates, it's exactly the same pictures I've already shown you, is that you just say, well, the rate of going back and forth, if it's classical, is proportional to the exponential of minus u divided by kt. If it's quantum, oh, sorry, this is doing a thermally activated rate, right? And so then again, at low T, the rates are really, really low, so nothing happens. Okay, here are the rates, they're really small, nothing happens at low T. At high T, the rates are always 1 no matter what you do, because e to the minus 0 is 1, so the rates are independent of the drive. And at medium T is when you get an effect where basically a small change in either epsilon or T causes a big response. So that's sort of seeing in the equations what I showed you in the pictures before. All right, but now I'm going to do the same thing for the quantum case. To, again, take the pictures and turn them and put some equations in. Sorry. Okay. Classical, they're temperature dependent. And quantum, what happens is one of the rates is independent. So we call it W minus. So we're going to go downhill. So we're going to call it W minus. And that one's independent of temperature, but the rates obey detailed balance. So the up rate does have an exponential dependence. But here, the dependence is on epsilon, the asymmetry divided by KT. All right. And then if you work out the theory with these two different kinds of rates, the classical dependence and the quantum dependence, you get very similar phenomenology, only classically everything happens on the timescale of U. The barrier height, the height, the barrier, energy barrier between the wells, and quantum, it depends on the asymmetry. And from the point of view of theory, this is actually really, really nice for the quantum case, because when your temperature is so high that it's over the barrier, then the assumption that you can think of it as just one state is starting to break down. But with this asymmetry, it turns out that that approximation is very, very good. And so actually the model should be quantitatively accurate. And so we worked it all out. And what we found was that we could really do a more or less complete analysis of this problem. And again, what happened was this was the state of the art at the time. And again, a while ago in the last century, worked out that you could essentially solve the entire problem, including for strong driving, any modulation, any dependence of the rates, and you can reduce everything to more or less integrals. Okay, I actually have that in the end, but with any luck at all, I won't have time to show you any of those equations. Okay, so there it all sat, and we published, and then that was the end of it as far as we knew until.
Could I interrupt you for a question?
Yeah, sure.
How I need to think about this noise? Could I think about the system is coupled with harmonic oscillators?
Well, actually, in our original case, yes, that's what we did. I'll tell you what motivated the original work, which is, again, I didn't want to talk too much about my past, but you gave me the opportunity. There were some experiments that Brage, Golding, and Neil Zimmerman did back in the early 90s, which motivated this, where they were looking at actually exactly that. It was looking at atomic defects tunneling back and forth coupled to conduction electrons. So the actual system was a thin bismuth film. And as you know, it's like polycrystalline and whatnot. So it had two-level systems in it. And so what happens is that the resistance is high. And so because of universal conductance fluctuations, they could just measure the resistance of this bismuth film, and you could watch individual defects tunneling. And they were tunneling following exactly this model, like the Caldera-Leggett. You couple it to a bath of conduction electrons, which is equivalent to coupling it to a bath of harmonic oscillators. And from that, you could you get a tunnel rate with a fairly non-trivial temperature dependence and dependence on the coupling, but it's still a Markovian. There's a regime where the dynamics are Markovian, and that was actually our original motivation for doing the theory. But it just happened because of life. The experiment was never done at that time. And so we just published the theory and we went on with our lives. And then, like, much later, the experiment is done using a completely different system.
I see. So you could also think about it's inelastic tunneling. So
yeah,
you need to get up. You need to take energy from the base, and it is given by the distribution functions. How many transitions from the top level to bottom you have?
Yes. Yes.
Okay.
Yeah. And again, what happens is, but sorry, I'll be slightly pedantic, but again, the end of the talk is more technical. And if I skip it, I'm sure you'll all be happy. The point is that, like, when you have these wells, okay, they have energy levels in the wells. And if the asymmetry is small compared to the separation between those energy levels, then the two-state description is like perfect. Okay, it's only then the Markovian thing is the only thing you have to worry about. And if it's not, then it's like less quantitative, but still qualitatively extremely good. But there is a regime where it's quantitatively appropriate to use this model. Okay, because of the fact that the asymmetry is determining what regime you're in. Okay. And that's a statement of, like, if I go up if I go down, right, and I don't go through any other states, I don't, I just either go from the state to that state and all the energy goes to the bath. Okay.
Thank you.
Okay, so I hope that was clear. Well, I'll ask here, well, actually, I'll stop for questions in a little bit. Okay, wait, okay. Oh, actually, now is a great time to stop for questions because I'm going to go to actually, again, the recent experiments. And so then there's going to be much more physics of what the actual mechanisms are. So if there are any questions, now is a great time to ask them.
Any questions? Please just go forward and ask.
Sue, can I ask one?
Sure.
So I've done a bit of stuff on two-level systems and noise, etc. What's not? I guess what I'm wondering is what's the relationship with this when you're talking about stochastic resonance and close to this transition point? What's the relationship between that and the Landau-Zener effect?
Oh, okay. So that's a great question, and we're in the opposite limit where, if you think about it, sort of in a Zeno paradox kind of thing but I'll put it in terms of maybe this is bad, but in the Caldera-Leggett language, right? There's like a coherent region, okay, and then there's an incoherent region where, if you think about it as coupling to a bath, the bath is measuring the particle much more quickly than the tunnel rate.
Okay.
Okay.
Yeah.
And so then the point is, in that limit, it's Markovian. Okay. But if you're in the situation where you're coherent, then you do care about how long you've been in the bath, right? Because, you can think of it, it's almost like you can think of a harmonic oscillator, right? But, and if it matters what the phase is, then you have to keep track of when you started your clock.
Yeah.
But if on the other hand, you just measure it, once you measure it, you've stopped your oscillator, and then you don't care how long you've been there because it got measured, and that measurement sort of puts you into a state. Okay. Yeah. So this is absolute. And so then it's a question of like, well, what's the time scale of that? And the argument which I will make is that, in the experimental system I'm going to talk about, that's a very fast time scale. And so we're in this other limit. Okay.
Excellent, thank you.
And again, that's a sort of way forward of like, can you get to, but that's a separate question. Okay. Okay, so now we're now in the 21st century. And so now I'll tell you about this experiment, which is, beautiful, beautiful experiment. And I don't know this, you guys may know all about this, but if not, this whole line of experiments, there's a community of people working on them, and it's really quite, really beautiful what they can do. So this is a picture from Sebastian Lowe's webpage, and Gregory and Max were the students who were driving the project. And this is artist rendition, obviously, of what's going on, and this is an STM tip. These are the atoms on an STM tip, fine, okay, and it's magnetized, okay, and then this green thing is an iron atom, and then there's a substrate, and one of the tricks in this business is to find the right substrate, because it turns out that the relaxation of these atoms depends very sensitively on the substrate. And so you want to get the dynamics into a frequency window where you can resolve everything. Okay. And what they found is that, like, this copper nitride surface, the spin relaxation is quite slow. Okay. And so then you can actually resolve individual transitions. So this SCM tip is magnetized. Okay. And so basically the current, so you apply a voltage, you go to the atom, you apply a voltage, and then you measure the current. That's the experiment. Okay, and the current that you measure depends on the spin state of the atom. So so this is relevant to single atom memories, doing spintronics, and having like a really long spin lifetime is good because if you're thinking of it in terms of magnetic memory. But here it's this idea of, you want to manipulate these things, and they started asking the question of what happens if you modulate the drive being the voltage. Okay, and these things are these sort of orange lines are, they're supposed to be electrons tunneling from the tip through the atom, iron atom to the substrate. Okay, just so you know. Okay, and so I'm going to have this thing happen a lot. This is again just the schematic of the experiment. Again, everything has to scan around, but you apply a voltage, magnetized tip, and then the red things are electrons, and they tunnel to the through the atom to the substrate. Okay, and then but then also there's all sorts of stuff that happens when you change the voltage. You create electron hole pairs, and there's quite a lot of theory about what the rates, how the rates depend on exactly what the voltage is. But for purposes of this talk, I'm just going to say you could measure it. You could measure the rates, and so I'm going to say the rates are known by either by measuring them experimentally or by some other theory that I'm not going to do. Okay. So anyway, so here's like there are two spin states. One is lower, one is higher, and again, this is what they measure. Is they measure, like, again, the conductance as a function of time. And here there is no drive. It's just going back and forth. Okay, this shows you. So what you're going to see later are these sort of everything's going to look perfect. But this is to show you what the data actually look like, and then they thresholded and filtered it, and they have a known response function for their apparatus, and so they can do quite accurate thresholding and from getting from here to here. They can do really quite accurately. So this is no modulation, and then this is with modulation. Okay, and you can see that if you put on a modulation, you see a significant difference in the traces that you get, and the whole rest of it is analyzing these traces. But from here on out, I'm not going to show you any of the actual voltage data. I'm going to show you the analyzed voltage data. Okay. All right. So one of the things that they found, and this is sort of the new physics and sort of why stochastic resonance suddenly appears in the system, is that they noticed when they did their analysis that one of the rates, the downhill rate, is independent of the voltage they apply, but the uphill rate is strongly dependent on the applied voltage. And again, the voltage is just the voltage between the tip and the substrate. And so the point is that that if you think that there was an effective noise, so this is not the temperature of the sample, but rather a noise mechanism that, as long as it's Markovian, though, you can sort of think of as absolutely equivalent to a temperature in the context of this theory. So what happens again is that these things act as a noise and cause the up rate to be strongly voltage dependent. Okay. And that means you can modulate the transition rates. And it happened again, I did the seminar and I said, what do you want to know? We can calculate everything. And because the theory we had worked out actually only cared about having transition rates. It did not care whether it was the noise was thermal noise. It works for any kinds of noise as long as the dynamics don't have memory. Okay, so this again, they tried to get into a glamour journal. So there's a fancy graphic, fancy schematic. But the idea here is, again, this is the STM tip, and then these are the electrons going through the atom to the substrate, and what happens is that the same drive that drives the transition rates. Okay, so it actually changes the dynamics, but then also you at the same time you just measure the current and you measure the dynamics at the same time. Okay, and this again is that picture of what the experiment is. Okay, I added that just to keep you oriented. Okay, and so then again, what you can do is you can analyze, like, as a function. There are two ways to do this, and one way is to actually like take your data and bin it up and measure the rates. And I think that's what they did here. The other one is you could measure in DC and assume the heating effects are small, and you can just measure the rates as a function of voltage. And it turns out in this experiment, it doesn't matter which one you do, you get the same answer. But basically, so let's sort of talk about the other one. As a function of time, the applied voltage. And so during the period, you have, different, we'll do this rate because this is the one that varies, right? You have different rates just because the voltage you're applying is different. Okay, and the voltage, the rates as a function of voltage, the voltage is a function of time, so the rates as a function of time in the drive period. Okay, so that's the simplest way of thinking of doing it, but you can actually extract it directly from the data. which we did to check that there wasn't heating or something that was causing something untoward to happen. Okay. So, so now again, this is the analyze data, analyze the way that I told you before. And then, so this is the drive. Okay, the drive is up on this side. And this is just that, you took the current that you measured and you defiltered it and thresholded it, and then you know what state you're in. And now this is as a function of the period of the drive that you're applying, keeping the drive fixed except for its frequency. And what you can see is that, like, if the drive period is long, if the drive frequency is low, then the rate does go up, but you don't get synchronization. You obviously see effects of the drive, but the response is not synchronized to the drive, because you get like 3 or 4 transitions when that slow rate is maximum. And if the we'll go to here, if the drive is really high frequency, then again you're not synchronized to the drive, because you still get several drive periods before something happens. But if your drive is at the right frequency, then one of the transitions synchronizes. So the down transition doesn't synchronize because the down transition doesn't depend on the drive, but the up transition, so you go up here at the drive maximum, go up here. This one didn't work, but you go up here, you go up here, you go up here, and so the up transitions synchronize to the drive. Okay, and that's the quantum stochastic resonance. Again, quantum because it's a quantum system, and stochastic resonance because you're synchronizing the response to a drive. Okay, and again now, and so after drawing the pictures, I just constantly stress that we can do really quantitative things here. Again, you take the measured transition rates as the input. Okay, but you measure them, but given those, we can predict all of the usual quantities that you use to characterize stochastic resonance with no approximations. Okay, and so this again is what's measured. You look at the time between successive up events. All right, and if you don't drive, you get a broad peak, and if you are driving, you get a narrow peak. And then you can ask, what's the fraction of time that you're in that, when you're near the drive frequency, when the time between successive up transitions is close to the drive period. And here is, and that's what they call the synchronization efficiency. Oh, and I forgot, again, as a theorist, this is important to me. This is the theory. Okay. And again, we use the measured transition probabilities, transition rates as a function of time, and you put those in, you just do math, no physics involved, and then you get, once you have the theory, you can solve it exactly, and then you get this with no adjustable parameters. And again, it agrees perfectly, but that's just a statement about the dynamics are Markovian. Okay, the relaxation processes are much faster than the drive, which is not so surprising because the drive's a kilohertz. Okay, anyway, but back to the synchronization efficiency, you got something, or for these parameters of order, maximum efficiency is like a third. And again, and then because we have an analytic theory, we can, we can sort of, figure out where the maximum is, and we can try to optimize it. But certainly, we feel like we know what's going on, and certainly the signal to noise also is enhanced. Okay, so the resonance part of it, which could be relevant in the spintronics context, also occurs. Okay, so I have time to tell you the theory. So let me stop for questions again, because here's where the equations are. And so if you don't want to see the equations, if you have any questions, now is the time to ask. Dimitri, you're muted. Yep.
Yes. Do you have any questions? Please just go forward and ask.
Yeah, just go for it.
I have a question. So in equilibrium, if you have a BESS, you have a detailed balance relations between probability up and down. am I correct that this presence of drive, it breaks these relations and strongly modifies them?
Yeah, so it depends on, now you're asking a question about in general versus the specific system. And actually, let me go back to the, the old days of the defect in the, just looking at individual defect in a metal. So there, what you can do is, it turned out in that experiment, and this is, by the way, now you'll know why the experiment was never, why the AC experiment was never done. The asymmetry turned out to depend on magnetic field. Okay, and so in principle, you could modulate by driving the magnetic field. But I've since learned by talking to many experimentalists that nobody likes to vary the magnetic field if they can avoid it. And certainly driving, a bulk magnetic field cryogenically is sort of not popular. So just letting you know, that's why the experiment was never done. So you could do that, or you can modulate the temperature. Okay. And if you modulate, so let's actually think about modulating the temperature. So if you do that, then again, then this idea of like, okay, I'm going to heat it up. Have I reached the new equilibrium? If I have, then the theory is good, right? Because then you're obeying detailed balance at the new temperature. Okay. So you certainly can drive it where the temperature is time dependent, but still completely well-defined. Okay. And that's one way of doing things. In this system, the, excuse me, in this thing with the STM, they've actually varied the temperature. Okay, and things do depend on temperature, but clearly there's the temperature is not the temperature of the experiment. Okay, the effective temperature in this process. But what the theory assumes is not that the rates obey detailed balance. It just says, you give me rates and I'll tell you everything you want to know. And as long as the system's Markovian, then the ratio of the rates could be used to define the effective temperature, because there are only two states, right? And if you take the ratio and the log of that, that tells you epsilon divided by KT effective. Okay, so it turns out whether or not you're in equilibrium is not an issue at all. Okay, but then of course the actual calculation of what the effective temperature is an issue. Okay, so that's why I said that we look at the rates that, we assume the rates are measured. We don't try to calculate them from first principles. But there is actually a lot of work in this system of the individual iron atoms on substrates where people do calculate these rates. And then absolutely you have to calculate the effective temperature from first principles involves the coupling to the bath and the time to equilibration. Okay. So again, to solve the whole problem is complicated, but if the dynamics are Markovian, you don't have to solve the whole problem if you're willing to take the rates as experimental inputs. Okay, but they can be time dependent as long as the time scale of the variation of the drive, from the drive is slow compared to the equilibration time. Was that clear? I'm trying to make, it's an important point. Because being in equilibrium, it turns out not to matter.
Okay, thank you.
Okay.
I try another general question, please. Yeah. So I think what you said was that the signature of a quantum stochastic resonance is that the rates in one direction are highly dependent on the temperature, and the rates in the other direction are independent.
Yeah.
Is that an absolute definition of a signature of a quantum stochastic resonance? I mean,
I see. Yeah.
Are there other processes which have that kind of behavior, which are not quantum stochastic resonances? So, for example, I'm thinking about things like random telegraph noise. Working from memory, I suspect that in one range or the other, you can engineer a situation like this just by having kind of asymmetric potential.
Yeah. Yeah, well, this is the thing. And again, it was just sort of a historical accident that when people thought about stochastic resonance until, in classical systems, the asymmetry doesn't come up. You know what I mean? It's like, oh, you got to get over the barrier. And so the thing was that quantum systems, so in some sense, this quantum versus classical is historical because originally everyone looked at symmetric systems, and there, if you have a quantum system, there's no effect. Okay. And then, and the theory that we worked out is completely general. I mean, it works perfectly well for classical stochastic resonance. The only thing is that in that case, the actual use of this transition rate theory is suspect because the max, sort of the interesting regime is where the transition rate theory itself is breaking down. So the other thing which is new is, again, new, since Parisi, more or less. The other thing which is new is this idea that it's a quantitative, that you can do everything quantitatively, that it wasn't just an analog or, an inspiration, like, oh, here's a simple model, but of course it's not the Earth's climate. You see what I mean? It was like, no, here's a system where you can calculate quantitatively what you expect to see in a specific experiment. Okay. And again, it was because that the theory in the classical case is being applied in a region of dubious validity, whereas in the quantum case, you can find systems where it is quantitatively accurate. And so in some sense, that's the only difference, is that the rates are in a regime that quantitative theory is applicable, and those systems tend to be quantum systems. But I'm sure you could find other systems where that was true. Okay, so I hope that answered it. Okay, because you're absolutely right. Because in the end, the theory is just I take two rates and then I do some math. Okay. But the systems that tend to have rates that don't, in the symmetric case, don't do anything are quantum systems. So I'd say that's my answer. Okay. But then the point is the small asymmetry then becomes, becomes dominant, and then that is what makes the theory quantitatively applicable. All right. But you're absolutely right. I mean, it's completely general. Okay.
Yeah, thanks. I mean,
again, I know this too well. I'm not doing a great job of explaining it, perhaps, but
I might get in touch by email and run something by you that we've seen in our experiments.
Oh yeah, no, and the thing, I will tell you, if I can calculate anything, if the model applies, then I know exactly what to do. And that was the thing with Sebastian. It was like, well, what do you want to know? It was like stupendous as a theorist to be able to do that. Usually experimentalists come to you and you're just like, wow, that looks really interesting. But every once in a while, you're actually able to help them and do something for them. So please be in touch. Okay.
Okay. Can I ask a question?
Yeah, sure.
So can you expand a little bit briefly your assumption of the rate being independent of the memory of the state?
Yeah. Okay. So yeah, and that's the main thing. Okay. So and again, what to say about it? The original motivation of this atom is actually really very to me easy to visualize. So I'll tell you that. So and again, this is this Legate caldera. You have like, it's called the spin boson model, but you have like an atom, and it can tunnel back and forth between two different places. Okay. And it's constantly getting, collided with conduction electrons. Okay, so that's one way. Okay, that's one way of thinking about it. And actually with the iron spin, this is a very good picture. Okay, but the atoms I like even better because there's no STM tip. It's just you have this atom, it's moving back and forth, but it's constantly getting hit by these conduction electrons, and they're the bath. Okay, and if the collisions with the electrons occur like really fast compared to like going back and forth, then what happens is that it just sort of like, it gets collided, and after a while it just hits some, it just relaxes to, a local steady state. It just sits there. Okay, but then when you move over, like the charge moves, and then there's like a cloud of electrons that has to follow it. You know what I mean? And so like the collisions aren't exactly the same until it's been there for a while and the electron cloud can relax. Okay, so there's a time scale corresponding to, I make a transition and I want to know what the transition rate back is. But I'm assuming that cloud has already made it over. Okay, and again, you can estimate those time scales, and again, you can do the analog for this iron, the iron atom spin, and your estimate is that things should happen on gigahertz frequency scales, and these measurements are kilohertz frequency scale. So you're like, oh, okay, well, whatever relaxation happened well before my transition back happened. Okay, so I don't know how long I've been there. All I know is it had enough time to relax. Okay, and that's the regime where the theory is valid. I hope that explained it, right? There's some process after you make the transition. It has to find the new normal, and there's a time scale for that. And if that time scale is short compared to your transition rate, then Markovian theory applies.
Okay, thank you.
Okay, so great, so I'll just show you equations just so you know that they're there. Okay, so this I showed you before, right? Where again, this is like, I'm looking at the excited state versus the ground state, and so the probability in a given time that you go into the excited state is, there's a rate that you go uphill, so it's the slow rate times the number of the probability you're in the ground state, minus because these are the guys leaving, it's the fast rate times your probability of being in the upper state, and then you use the fact that you have two states. Okay, and so that just says NE is 1 minus NG, and so you can write the whole thing as a differential equation in terms of one variable. Okay, and again, it's only a first order differential equation, and that's where the Markovian process comes in. And again, for some reason, I don't know, is that people just hadn't noticed that you actually can like solve this, essentially completely exactly. And so, and then it's just a question of, writing formulas. Okay. And I think it's late enough that I won't go through it, but it's totally interpretable in terms of like things that you would expect, like, what's the probability you're in the state at that moment, and then there's some probability that you make a transition, and then there's some probability that you didn't make a transition, and you work it all out and you get a closed form solution. Okay, it's there's integrals, but they're integrals over known functions. Again, what we're assuming is that what you know are these rates, and so everything, it's as you see, it's not trivial. There are 3 pages, but nonetheless, it's like a completely well-defined bottom line. Okay, and again, with the rates are measured, then there's no fiddling at all, because you can just do the whole thing. Now it wasn't trivial to do this though, because because it turns out that the integrals are only over one drive period, and so the fact that the whole thing could be resummed so that you only have to integrate over one drive period was not obvious, and that was what the intellectual content was, and the theory was realizing the whole thing could be recast over an integral over one period. Okay. So I just want to say, like, for me, it's a fun story, because you start with ice ages, and I spared you the crawfish neurons, and I mean, so a stochastic resonance is, really applicable to a lot of systems. And my contribution, I believe, is our contribution is to extend it to this other class of systems, and I think it will be equally broad. And that's why I'm all excited to hear about data that could be relevant. But in terms of like the immediate future and the collaboration with the Stuttgart group, I mean, one thing that's actually we did a little even in the paper we published is that once you have a theory like this, you don't have to resolve the individual transitions if you believe the theory, which in the regime where they were able to measure, the theory works perfectly. So you can push to higher frequency and use the theory to so you modulate at high frequency, but you measure in the frequency range that you can. And then you can infer dynamics on timescales that are much shorter than what you can resolve experimentally. And that is relevant to this Markovian thing, which we keep coming back to, is that once you can do that, you're able to then perhaps, we don't know exactly how far we'll be able to push, but this is where we're pushing now. We'll be able to figure out when the Markovian approximation fails. So in other words, what is the dynamics of that relaxation after you make the transition? And what's the time scale of that? And can we learn something about that? And so the theory gives you a window into high frequencies that you cannot resolve experimentally, but you can drive at those frequencies and measure at low frequency and use theory to make that connection. And then the other thing, which is super interesting, because there are several places in the theory where you use the fact that you have only 2 states. If you have more states, actually, then much more phenomenology could happen even in this Markovian regime. So I will summarize. Hopefully I've convinced you that stochastic resonance occurs a lot. Again, the classical stochastic resonance had already been known to occur a lot, but now we have I think really convincing evidence that in this particular system of iron spins on substrate, the phenomenon occurs. You get the maximum, you get this maximum synchronization, and also the theory is relevant. And again, assuming that the dynamics are Markovian in the sense that I've been discussing, if you do that, you can make theoretical predictions that agree well with experiment. And again, then we're pushing forward into being able to probe different frequency range and the validity of the theory. And then in the future, we're going to be able to use similar methods to look at more complex systems. And that's it. Thank you.
Thank you for great talk. Do you have any further questions?
Oh, yeah. More questions. Yeah.
You just go forward. Okay, I have a very simple following question. If you turn, so you have two-level system and you add the coupling. So if you turn off noise, I'm correct, you will just get a Rabi flopping, and the presence of noise completely reshuffles it to these peaks or transitions.
Yeah, here, let me see if I can do I'm going to stop the share. Oh, wait, here's a new share. Let's see what new share does, and we'll try the whiteboard. Okay. And also do the draw. Okay. Yeah, so this is sort of the thing that, again, it's a natural thing to do, but I haven't done anything on this, right? So the thing is, if you have, sorry, we're going to think about a classical spin. Okay. And again, there's some frequency which is there. Okay, so this is Z, and here's your spin, and it precesses around. Okay, and that's okay too in some sense. Okay, but you can have a spin up or you can have a spin down. Okay, and right. And what I've been assuming is that the noise processes work on a scale where you're either in one or the other, and you're not flopping. Okay, so actually maybe I'll do it sort of back in the day. Okay, so again, this is sort of like if you do Caldera-Leggett kind of thing, but let's not worry about Caldera-Leggett, but basically what happens is that there's some, we'll do it this way. Okay, if you have no coupling to the bath. Okay, and actually, let's just think about the symmetric system, because it just makes life easier. Okay, so here's a Hamiltonian. Okay, and then there's some off-diagonal term, which we'll call delta, which was probably a poor choice because these are supposed to be zeros. Okay, All right. So what happens is that then, you know, there are two states, and then you look at the energy difference between the two states, and it's 2 delta. Okay. So again, this is energy, and, you know, and oops, I didn't want to do that. Undo. Okay. This is energy, and then this is like, you know, the number of eigenstates. So this is like a density of states thing. Okay. All right. So in this limit where it's perfect and there's no bath, you have like a peak. Okay. Then you couple it. Okay. And then what happens is that for a while, you know, there's still a peak at 2 epsilon. And then this is just modeled as, you know, a decaying exponential, right? And that was sort of what Jared brought up also. I mean, this is a natural thing, but again, the theory is not set up to do this. So I didn't focus on it. Okay, but then if you keep coupling to the bath, then what happens is that there's then the point where, you know, the width gets broader, you know, it doesn't go to negative, but the width due to the coupling becomes broader than 2 delta. Okay. And that's the regime where I'm working in, where the bath is strongly coupled. And so all of the stuff that you normally think of as being resonant doesn't happen. So it's just like you have a harmonic oscillator, right? Where, you know, you start, this is response as a function of time. Okay. So this is just x of t. Okay. And, you know, if the damping is low, it oscillates, but there's a critical damping, which is finite, where it turns into a pure exponential. Okay. And once you cross that, then you don't know where you are relative to the drive because the decay is purely exponential. So I should have said that first. Okay, but that's the explanation. It's just that basically like there's a transition above which you really do lose memory of your past. You know, it's not like only in the limit, but there's a point on a phase diagram where you don't see the oscillation at all. Okay, and that's the regime where the theory works that I've done. The Markovian theory essentially works.
Okay, thank you. Okay. Do we have any other questions? Please just go forward and ask. If we don't, let's thank the speaker again.
Thanks, Susan.
Okay, thank you.